Alright, hi everybody. So today we're going to continue our discussion of enzymes, but we're going to move on to inhibiting enzymes. So why would you want to inhibit an enzyme? So this is something I've been referring to a lot. I can't help myself. I've been jumping ahead a little bit and talking about this. And the reason that you'd want to inhibit an enzyme is that many diseases arise from either deficiency or excess of one metabolite. Those are what we call metabolic diseases, or so those tend to be genetic diseases. An infestation of a foreign organism. So this is kind of a weird way of saying either a bacterial infection, a viral infection, or a parasite infection, or a fungal infection. So you might call it an infection rather than an infestation. It's a little dramatic word choice there. Sorry about that. Or many diseases are also caused by aberrant cell growth, and this is something we've touched on before when we talked about cancer, which is cells growing in a unchecked fashion. These diseases can be controlled by specific enzyme inhibition, and what this happens is that if it can't either degrade or can't form its product, then this can mess up a lot of the chemistry that goes into this specific disease. So it can end up killing cancer cells. It can end up killing pathogens or making an environment that's really hostile for pathogens to live in, or it can correct genetic diseases that are caused by being born with some variant of a protein that causes metabolism issues in metabolism, or at possible this can also be due to disorders that happen later on that also lead to excesses of metabolites. So we're going to go through a couple of different definitions here. Enzyme inhibitors are something that slows or blocks catalysis, but it's reversible. So it either blocks it altogether or it slows it down, but either way, it's a reversible reaction or a reversible interaction with the enzyme. And that's in contrast to an enzyme inactivator. And so that's a irreversible inhibitor. So that's something that irreversibly interacts with the enzyme. So I was saying before, they use that a lot in chemotherapy as that's what we call warhead drugs, and it's also used. We saw that was how Prilosec worked, that it turned off proton pumps that were pumping acid into the gut. When we use drugs to combat foreign organisms and aberrant cells, it's chemotherapy. Typically, the term is really only used in the context of cancer. Or that's really going to be the most common use of that term, even if it's correct to use it for antibiotics. So you might see it in the context of antibiotics, but it's most commonly used just to talk about cancer. So notice that about 1/3 of FDA-approved drugs, this is a little bit dated now, I need to go back and refresh this number, from 2006 to 2011 were enzyme inhibitors. So the ideal inhibitor is totally specific for one target enzyme, and this rarely occurs. What we need to do is we need to look for differences in metabolic pathways between a foreign organism and humans. We need to look for differences in substrates. So these are three different techniques now. So looking at differences between metabolic pathways between a foreign organism and humans, this is saying, okay, let's say this bacteria that causes pneumonia makes a cell wall that's different anything any of human body cells make. So if we could inhibit an enzyme that makes that bacterial cell wall, we might be able to kill that bacteria and not kill any human cells. The second one is looking for substrate differences. Again, this is saying, well, if there's something wrong with this enzyme and we don't want to hit other enzymes in the body, is there a substrate that we can look for that's different? Is there something that makes it different than the usual substrate? This is really challenging with tumor cells because tumor cells are your own cells. They've just mutated in key genes, and so they'll rapidly. One of the things though is that they're growing really quickly. They're growing very rapidly, and so we use that to our advantage because they're really tough to deal with because they're so similar to your cells and many of the ways that a medicinal chemist would look at it, or many of the ways that a biologist would look as well. But they just have these dramatic differences. And so we have to take advantage of them, and the way that we do that is selective toxicity. But as you can probably guess from the first line in this slide, selective toxicity is only so selective, right? Chemo is generally, we all know that it's not considered, it's certainly not considered a walk in the park, right? So when we're designing antibiotics, we're designing drugs to target the survival of the microorganism. And so we want to pick something, again, that's unique to the microbe so the humans are not harmed. That's conserved across a variety of species so that it can be a broad spectrum antibiotic. You generally are taking broad spectrum antibiotics either for gram-negative or gram-positive bacteria. We'll talk about that in a second. And we hope that resistance is not easily acquired. Now notice this last point. It generally takes 1 to 4 years for resistance to emerge, and you can actually do these studies in the lab. You can add a certain amount of drug to create this pressure on the enzyme, or sorry, on the bacteria, so that it begins to evolve resistance, and you can see how long it's going to take because bacteria will always evolve resistance, and it's just a matter of time. And so what we're doing when we create these drugs is we're just buying ourselves time essentially in the fight against this bacteria, and eventually the bacteria will evolve a resistance to whatever drug we're using. And so that's why there's these first line, second line, etc. antibiotics. For example, it used to be that penicillin would kill everything in the 40s and 50s when it was first used. But really by the mid-50s, they were already seeing penicillin-resistant bacteria start to pop up. And now most bacteria are resistant to the original line penicillin drugs. And similarly now we have things like Cipro, antibiotics like Cipro and vancomycin that are really good antibiotics, but we already have resistances to these antibiotics. And so there's a lot of attempts to control how antibiotics are prescribed because this resistance is inevitable. And if we don't have, let's say that it's the last line antibiotic, if we don't have another antibiotic that's past that and people are prescribing this last line antibiotic whenever they want, then we begin to have a problem because we have disease varieties that are basically resistant to any drug that we have. Okay, so the ideal enzyme target in a foreign organism or in a cancer cell is one that's essential for growth but non-essential in humans, or not even present in humans. So that would be, here we gotta say that'd be something like totally mutated enzyme in a cancer cell. So that's what we are looking for. So again, this is my cell wall example that with some cell wall that humans don't make. And so again, reversible, this is typically non-covalent, and irreversible, it's going to form a covalent bond. Okay, and reversible enzyme inhibitor, so here you go to the supplementary video. Okay, I'll just stop it